So one thing that also gets computed when you do a vibrational frequency calculation is not only the frequencies of the vibrations, but you actually get a lot of thermochemical information as well. And so if we go here, right, and we look at for acetaldehyde, the output file, right, one thing you can see under calculated quantities, right, it gives you the total thermal energy, right, the total enthalpy, the final entropy term, and so forth, right, and so you can use that information, and these numbers right here are given in what's referred to as Hartrees. So we go right here, right, to output, and we scroll all the way to the bottom, right, you'll get all these different pieces of information as well. Right, you can directly pull out the enthalpy right here, and so what it does is it gives you what the energy is, and also then all of the corrections that are necessary, right? Because you have to think about the 0 point energy correction in these instances, right? The entropies of the various components, right? The electronic, vibrational, rotational, translational, and so forth. How all of those add up, and then from there, right, you can get the Gibbs free energy. Now, one thing I want to point out about the Gibbs free energy is that this right here doesn't directly match what you would get like from a textbook, right? Because in the textbook, right, the values that we typically use are all referenced to, the elemental states. The calculation doesn't do that or anything, right? So all of these are relative. And so when you're doing a calculation and you're taking the Gibbs free energy, you can really only compare the Gibbs free energy from one, computed molecule with another computed molecule if you're using the exact same combination of basis sets and functionals, if you have the exact same number of atoms, if the charge is exactly the same, right? And then all the different atom types are exactly the same as well, right? So all those have to be the same. So you can use, DFT to essentially compare the stabilities of different isomers and conformers, right? But you have to make sure that all those different parameters are correct. Now, if we're looking at it right here, right, what we can see is we can get the, the total, Gibbs free energy minus the electronic energy right here, right? So that's given as, the, these different values. And so we, can pull that directly out of here, and we can start comparing that to what we have. Now, one thing to point out is that for computations, the electronic energy for lower level computations is usually going to be not that great of an accurate value, right? However, the thermochemical ones, even at low level computations, right, those can be useful. Now, this electronic energy, right, is the single point energy that I've pointed out in the past. And so if you were to, run those same calculations, but not doing the vibrational calculation, but getting the single point energy, right, you can then, subtract that out of this final Gibbs free energy value that you have right here, and you can get a pretty good value. But for now, all we really need to do is just simply, we can take these values that we have here. So since it's already converted into something that is much more useful and worthwhile, right, we can take this value that we have here of kilocalories per mole, and so we can see that for the acetaldehyde, the Gibbs free energy is 19.42 kilocalories per mole. So if we put that into here, right, we can just simply use an Excel file, so that way we can standardize everything and see how the different isomers, right, compare with each other. So we have this for the acetaldehyde. Now, if we look at our other calculations that we had done for the vinyl alcohol at 0 degrees and then also at 180 degrees. So if we go first to the 0 degrees and click on it, and we go to raw output, we can scroll all the way to the bottom right, and we get right here, right, that energy is 20.07. So we just plug that in here. And then finally, right, we can look at the 180. Go to raw output, and then scroll all the way to the bottom, right, and we get 19.69. Right, and so these are all the different values in kilocalories per mole. Now, what we can do, right, to if we're going to be presenting this, or if we're going to be showing any kind of comparisons, we can standardize it. We can always standardize it, for the most part, it makes the most sense to either the one that specifically, or just simply the lowest one, right? And so looking at this, we can see that the acetaldehyde is the lowest. And so if we're just going to standardize this, right, we'll just simply do the value that we have minus the value that we have that we're standardizing it to. And just to make our lives easier, right, we just put the dollar signs before the B2 right there, so that way it all stays the same, and you can just pull it down. And so now we can see the relative stabilities in kilocalories per mole, right? So we can see that acetaldehyde, is about 0.27 kilocalories per mole more stable than the 180 degree vinyl alcohol, and it's about 0.65 kilocalories per mole more stable than the 0 degree vinyl alcohol, right? So the difference between the cis and the trans species. We can also then see right here that, the cis species, right, the 0-degree vinyl alcohol is actually the least stable out of all of them, right, that it would prefer to have that hydrogen oriented away from that carbon. So that, is one really useful tool that we can use for DFT, is figuring out which isomers, which conformers are actually the more stable one, so that we can use that information to try and, calculate other properties that hopefully match our experimental data more closely.